Hey, welcome back to Math with Patrick. It's April 12th, and we have problem number 102 from this Daily Epsilon calendar to solve together. So the answer is supposed to be 12, and when I do 8 times something squared, I'm going to get 12. So I guess one good thing to check first is just what value am I going to get from sine of pi over 12 plus cosine pi over 12? Because this chunk feels like the hardest part for me. Let's see. So looks like x squared is going to be 12 over 8. I could reduce that fraction just a touch to get 3 halves. And so it looks like x is going to be the square root of 3 halves. And I just need to set out and prove how I can make this the same thing as the square root of 3 halves. I think what I want to do first is take this and treat it as a function, as in I could put in any input here, and then try to simplify it. I know that with trig functions, there's a lot of different ways to combine and rearrange them with trig identities, but I don't really know a trig identity for, oops, that's supposed to be sine of x plus cosine of x. However, I'm going to try it graphically and see if I can get some kind of other representation for that function. We're starting with sine of x plus cosine of x. And to me, it just looks like any other normal sine wave. Like here is just the normal sine wave. And the black one is a little bit taller and it seems to be shifted a little bit maybe to the left. And so using graph transformations, I can stretch it vertically. Let's see. So currently the sine function reaches the value 1, and this black curve reaches this value of like 1.4. I know that value to be the square root of 2, actually. So if I put a root 2 here, a multiplier at the front of my function, it's going to stretch it vertically, and now I'm matching the same height or amplitude as this original function that I'm trying to match. Now, it looks like if I just shift it left a little bit, I will line up perfectly. I mean, I could shift it right, but that would be kind of far. So currently, this maximum is at pi over 2. The maximum I'm trying to hit is at pi over 4. And so if I had shifted left pi over 4 units, that would be like, let's see, I can do a little animation here, where here's where it was originally, and if this value that I'm adding to x right here is pi over 4, it's shifting that red curve right on top of the black curve. And so I know that that's supposed to be pi over 4. So let me take this representation back to the whiteboard and see if it's helpful for today. Now that I know that sine of x plus cosine of x is the same as this expression on the right, all I really need to do is plug in pi over 12 for all the x's that I see. And I'm going to hope that I get something a little bit easier on the right side. And I mean, what I mean by easier is that there's some usual angle measurements that you plug into sine and cosine functions. Usually they're going to be pi over 6, pi over 4, pi over 3, and pi over 2. These correspond to 30 degrees, 45, 60, and then 90. And all of those are like fairly easy angles to plug into these trig functions. Pi over 12, however, is a little bit weirder. I mean, maybe I could relate it to that pi over 6 value. That's probably another solution. We could do something with like half angle or double angle identities, but I don't know. Maybe that's for you to try or something. So here I'm just replacing all of my x's with pi over 12s. And let's see what pi over 12 plus pi over 4 is. That's going to be the same as just pi times a 12th plus a 4th. And then to do this fraction addition, I'm going to find a common denominator of 12. Looks like I should multiply the 1 by a 3 as well. And then I get 4/12, which is the same thing as 1/3. So ultimately, those two fractions add together to get pi over 3, which is one of those like easier angles that I was talking about. So this is going to be equal to root 2 times sine of pi over 3. And let me show you why it's maybe an easier angle to deal with than the pi over 12. So let's see. I'm going to draw a unit circle. That means the radius is going to be 1 right here. And pi over 3 is the same thing as 60 degrees. And so I'll draw it like this. There's pi over 3. That's just because like the whole circumference is going to be 2 pi. There we go. That's a pi. Close enough. And so if you add up all of these pi over 3 angles, you're going to get 2 pi. You could also double check. You could add up all these angles as thinking about them as 60 degrees, and you're going to line up with the 360. That's kind of conventional for a circle. So however you do it, pi over 3 is going to be the same angle as that 60 degrees. And here, I'm going to think about drawing a right triangle right here. And again, maybe I'll put the angle here. This is going to be 60 degrees or pi over 3. And it's basically like I just drew half of an equilateral triangle, kind of like this, where I guess this is still a 1 because it's the radius of my circle. And then I basically perfectly split this equilateral triangle in half. So I could have a half here because it's half of this radius. And then, let's see, how am I going about this? I want to figure out what sine of pi over 3 is. The angle pi over 3 is right here. And the sine function tracks the opposite side divided by the hypotenuse of a triangle. That's just kind of like by definition. And so sine of pi over 3 should be this opposite side divided by the hypotenuse. And well, the hypotenuse is just 1. And so this value right here is going to be the same as sine of pi over 3. And finally, I can employ the Pythagorean theorem to solve for this value. I know that a squared plus b squared is going to be equal to c squared, the hypotenuse. So let me square everything. 1 times 1 is 1. And then 1/2 squared is a fourth. And I'm going to subtract that fourth from both sides, so I get some equation that looks like this instead. B squared is equal to 3/4. And so when I square root both sides, I could square root the top and the bottom, and ultimately that root 4 turns into a 2. So maybe you already know your values of sine and cosine, but I just wanted to like double check, go through all the work, and really show where this is coming from, that this value right here, sine of pi over 3, is exactly the same as half of the square root of 3. So let me make some room. How about I'll go over here? This is going to be equal to root 2 times root 3 over 2. And I guess I could combine my square roots where I get root 6 over 2. And that should be the same value as this. They currently don't look exactly the same, but maybe if I turn this back into a root 4, and then I hug the whole thing in a square root. And this step isn't completely obvious. Like, it shouldn't be taken for granted that dividing square roots is the same thing as taking the square root of division. Some operations out there are less friendly and they don't kind of do this the same way. Like, for example, the square root of a sum is not the same thing as the sum of square roots. So when you're employing these algebra steps, you got to be a little bit careful of what you're doing and know not to do the other things. But I know this to be true. And then finally, I could simplify 6/4 as 3/2. So I have shown that this value is indeed the square root of 3/2. And that basically proves that the number is 12. But let's just run through the math real quick. We're going to do 8 times square root of 3/2 squared. The square root cancels with the squared. And then finally, I'm noticing that I could make a 4 out of the 8 and then divide by 2, and then 4 times 3 is 12. So there we go. Cool. Well, I kind of enjoyed being able to use graph transformations a little bit to come across an easier value for sine, because I don't really know sine of pi over 12 that well. And then ultimately, plugging it back in gives us 12 today. So we're all done. I'll see you tomorrow. Thanks for solving this with me. Bye.